Okay, great. All right, why don't we go ahead and start? Thank you very much for taking the time on a Friday morning. I wanted to just have a quick demo of Platform because it's new. We're not sure we're explaining the technology correctly on our website yet, since it's new. And really, I wanted to keep this interactive, have you ask a lot of questions and also provide feedback, both in terms of how we're presenting the tool and the tool itself, the content of the tool itself, the usability. So I'll give you a little bit of a history of how this came about, our genesis story. We'll do a quick demo. I'll walk you through a couple of use cases. And then also wanted to share some of our blog posts in research areas that might be of interest as well. So why don't we go ahead and get started? In terms of our team, the idea really came from Jeremy Howard. He is the head of research at Fast AI, the author of a very popular machine learning library that sits on top of PyTorch. Previously was the founder of Analytic and chief scientist and president of Kaggle. Obviously someone that's very much a hands-on practitioner and someone that cares a lot about bringing useful tools to the machine learning community in very practical, pragmatic ways. My background, most recently, I founded Launchpad AI and Fellowship AI. That's a program that about 140 people have completed. It's available worldwide. It's a 4-month program to get hands-on experience with advanced AI methods, followed by lots of commercial engagements. And that organization now works with the largest telco, largest insurance company, large retailers, et cetera. So it's a fast-growing organization all over the world and also partners with Platform to help us with some of the research areas. And then before Launchpad, I was chief technology officer for Sentient Technologies. That was an AI hedge fund and did some marketing analytics as well. So the way this got started is I met Jeremy for coffee one morning and I said, hey, I'm experimenting with embeddings as a way to assist domain experts to label data. He said, hey, have you seen my TED Talk? I gave a TED Talk in 2014. Called The Wonderful and Terrifying Implications of Computers That Learn. And he said in there, I actually demonstrated a prototype tool that we built when I was at Analytic to help with this kind of labeling. And I said, this is incredible, Jeremy. This is a really interesting idea. Is Fast AI going to build that tool? And he said, no, we're not. We're building a library on top of PyTorch. But if you want to go ahead and build it, I'll help you. So that's all it took. I think we incorporated the company right after that conversation. So it was something that I was very, very excited about because I hadn't really seen any tools that domain experts could use in the AI world. Everything that's been productized was really geared towards researchers and data scientists. So let's talk a little bit about what problem we're trying to solve. Deep learning, machine learning requires lots of data. In order to get that data, the typical thing to do is to go out to crowdsourced workers, give them your data set and have them label it for you. You can do that with Amazon Mechanical Turk. There are specialized companies like Crowdflower, Figure 8, Mighty AI, et cetera, that label data for you. And interestingly, this was like the top of the backlog maybe about 6 months ago, Mechanical Turk. And what we noticed a lot of crowdsourcing, essentially, people are crowdsourcing image labels. So you can see some examples here, determine if my image is blurry, get some information out of these receipts that I have photos of, et cetera. And in fact, when we looked through kind of the entire backlog, we noticed that 2/3 of what was on there were basically image tagging tasks. Which is fine. I mean, this can get quite costly. Obviously, you're paying anywhere from 3 cents to 8 cents, sometimes even more per label. And as long as you're dealing with kind of, use cases that any novice user is familiar with, this works, and you have the budget to do this, this works. But what if you're working in a very technical domain? You know, you're a scientist, you're someone that works with GIS data, geospatial data, aerial data, you're someone that works with, you know, very technical, let's say like PCB boards, etc. I can't send this kind of data set to Turkers, mechanical Turkers, and say, label it for me. In fact, I had this same exact experience when I was at Sentient. We were building a fashion product, and we could send data sets like, you know, are these two pants similar? Are these two jackets similar? Are these two shoes similar? And we would get pretty reasonable labels from the Turkers. As soon as we gave them something unusual, something that requires a little bit of domain expertise or expert eye, like rugs, we would get back, you know, very inconsistent results. And those results, those labels could not be used to train a model because, you know, there's a lot of disagreement amongst novice users as to do these two rugs look similar. So imagine going from rugs to something that requires, you know, 10 years of education to label a data set like this correctly. I'm just going to pause there, let you ask any questions. Again, you can ask a question by typing it into the chat window here, or obviously just unmute yourself and stop me. So we want domain experts to label their own data, essentially. So what's the problem with that? Why is that a hard thing to do? You know, deep learning requires lots of labels, not just a handful. If you put a domain expert in front of a spreadsheet and say, please label this for me, you know, they'll give you very few labels because it takes some time to think about the data set, the images they're looking at. It's a slow process, right? Like a few hundred labels might take a domain expert a few hours, so it's not very scalable. And as I said before, this is not something that you can parallelize. It's not easy to go out and find somebody else that can help you do this labeling. So this is essentially the central problem that platform AI is trying to solve, is how to overcome these three issues. So let me jump over to the UI and maybe show you a couple of use cases. So we'll start with something really simple. This is a data set called STL. It's used for few-shot learning. It has 10 classes. It's very close to ImageNet. So what I'll demonstrate is not going to be amazing, but I just want to show a really simple example, and then we'll make it progressively harder. So I'm opening up this data set. This loading part takes a little bit of time in our tool currently. What we have to do is we have to random sample our collection of images, run those images through a pre-trained network, get the activations out of that pre-trained network, do some dimensionality reduction, take the essentially projections that we see come out of that network, and pick the ones that we like, the ones that we think are useful, or the tool thinks are useful, and essentially present that in this UI. So what you're seeing here is a kind of a scatter plot of images, but you might notice that there's a pattern to the scatter plot. So you can zoom, you can pan different aspects of the scatter plot and kind of look at what am I seeing here? What is my, as an expert, kind of a human that's able to pick up patterns, what patterns do I see in these projections? So I can move around, navigate my data. I can zoom in on individual instances if I want to see those images a little bit bigger. And I have a lot of different perspectives that I can see this data from, because the data, when it's passing through a pre-trained network, gives us very large embeddings, anywhere from 4,000 dimensional to 60,000 dimensional embeddings, whereas the human eye can really process only two-dimensional visualizations like this. So we're showing you this very high dimensional space, essentially different perspectives. And we're hoping that as we change perspectives, your eye will react, it'll pick up on a pattern. And that pattern might assist you in labeling the data. So I quite like this perspective, for example, because I can see it's very clumpy. So I can kind of narrow in and see, what are these clusters about? Why did it choose to put all those images there? And I can do that by kind of zooming or panning, or I can just lasso them and bring up a gallery view of those images. And I can say, okay, I see what's going on. It's identified a cluster for cars. and it's misjudged maybe one garbage truck as a car. So I'll exclude that one. I'll say everything else in that cluster is a car. So what I've done is essentially labeled 38 examples out of my data set as a car. And I can see a few other clusters like that. There's one here. Let's see what that one is about. Pretty much looks like all birds. I added another class. Now we've identified 39 birds. And you should expect that things that are kind of similar should be pretty close together in this space. So in fact, I can see another cluster over here, close to birds, that are airplanes. And there may be some mistakes here as well. And sure enough, there's one that's gotten misjudged. It looks very much like an airplane, but happens to be a bird. So I'll say everything else is a plane. So far we've picked up 3 classes out of the 10 pretty easily. Let's see if over here, these things are probably right on the decision boundary close to cars. And yes, in fact, these are the trucks in my data set. You get the idea. I can lasso select these. I can increment. So I initially did my selection from this part of the space. Looks like there are a few more planes here. I can verify that those are in fact planes, maybe with the exception of a few things that have like a blue background, but it's confusing them. So this is very much the decision boundary between plane and ship, for example. So I can pick that up, add it to an existing class. I am going to want to label ships, so maybe I'll approach it from the other side of that cluster and see if I can pick up ships. And again, you can see like seaplanes are getting confused, which is to be expected. Okay, now I have my ships, or at least a few ships. And it's okay, you're probably seeing me make 1 or 2 mistakes as I do this. Like I think I inadvertently picked up, one here that's actually a couple here that are not ships. That level of noise should be fine for the algorithm. Let's see, and then we had a few animal classes here. I can go to this part of the data set, lasso this part of the space. Looks like all monkeys. Add that. There's another neighboring class here. Let's see what that is. Okay, so this is like a collection of deer and dog and cats, etc. So maybe I don't want to process this using this cluster. I'll go to some other perspectives and see if there's an easier one for me to pick up that trend. In fact, I see a really nice cluster of birds here. I'll capture those as well. You get the idea, essentially. I can walk around this space, pick different perspectives. It looks like this one may be actually much better at segregating some of the classes here. Let's see if this end of that cluster, a little bit of a mix. It's mostly horse. I can pick up, you can see it's like things that have kind of a horse posture as well are being classified as horse or being clustered for horse. So I need to exclude a whole bunch of these. Maybe you should have zoomed in a little bit before I went ahead and did that. Yeah, if I zoom in, then I can make much more precise selections. Like I think this down here, these little guys probably were. Yeah, those are all horses. You get the idea. So you are doing work, but you're doing work in a pretty fast way. And the idea is that once you've labeled a few dozen examples per class, you can ask the tool, train a model for me. Let's see how well you do if you just did an 80-20 split with the data I've labeled, use 80% for training, 20% as a holdout, and then tell me how well can you train a model just based on the examples that I've labeled so far. So it's train the model. And it's going to give us a new projection that's specific to the classes that we created now, because initially it was just using ImageNet weights. So it's getting new 500 images, processing it. Now it's processing it not from a transfer learning network, but the network that we've essentially trained. And that network already has a pretty high accuracy. You can see here 96.9% accuracy. And what will happen is the projection should keep getting better and better as you do this kind of labeling. You can see the clusters are even further apart and even more distinct, at least the ones that we worked on. The animal cluster, probably not so much yet because we labeled very few instances in there. If I do want help labeling some instances, let's say I want to create a dog class, I can pick up a few examples like this and I can say, go ahead and do a similarity search in the high dimensional space. I can't see the dogs very well. They're sort of mixed in with everything else, but see if you can just find things like that and only like that, those two examples that I asked for. Let's see if this brings up any useful results. Looks like someone has a question. Yeah, that's a really good question, Konstantin. It does depend domain to domain, but the tool has a goal that if you label just a few hundred examples per class, we want to be able to give you, let's say, a 90% accuracy model. Obviously, that doesn't always work. Sometimes we don't have good transfer learning networks to initialize from, but that is essentially our the tool's kind of stated goal. Yeah, we'll talk a little bit about some of the algorithms that we're using behind the scenes. In fact, that's why I want to cover some of the blog topics. Yeah, we'll get to that once we're done with a few of these. So anyway, we talked a little bit about that STL data set that, as I said, is pretty close to ImageNet. The next example I want to show you is something that maybe is not as easy for ImageNet to process. This is a real estate data set. These are images of different rooms as well as the exterior of the property. So what I would like to do for this one, let's try to load this again. Okay, maybe I'll bring up. We have some rate limits on our on the public edition of the tool. That's what I'm coming up against, I think. I'll choose a different project. Let's look at fashion for a minute while my rate limit on the other project expires. One of our objectives is to make the tool public, but unfortunately, because public usage can kind of overwhelm our system, we had to institute some rate limits. I forgot to mark these projects as private, so I wouldn't run into any rate limit issues. But this is a data set that, again, is pretty far away from anything ImageNet can cluster. So in this case, we're not using an ImageNet network. We have an algorithm that determines what's a better data set for me to use in order to give the user interesting projections. So you can see here, this is something that I'm certainly not an expert at, but you can see here that there is some clustering. These are pretty similar kind of athletic dresses with open arms. And if I go down here, maybe there's like a little clustering of things that are like flower shapes, different pattern dresses. Kind of, you can see that these look somewhat compatible, or they might have come from the same section of a retail store. And if I go over to maybe this part of the space, we'll see a little bit more formal, longer dresses, kind of more fancier outfits. And what I want you to notice is that this algorithm is not just like overfit on some aspect of the data. Like, it's not picking up the same model, although that does occur obviously in the data set. You'll see lots of different poses here. You'll see background differences, obviously model differences. There are some examples, like actually if we picked up the cluster, maybe like this, you'll see an image in here that doesn't even have a figure. doesn't have a person in it, but it is the same kind of dress. So it is doing something pretty interesting there to produce these clusters. Let's see, there was another question. Yeah, that's exactly right, creative AI. We automatically analyze the data sets and determine out of the pre-trained networks that we have at our disposal, what's the best one to use for transfer learning purposes without knowing what domain you intend to label. Okay, so let's go back to our real estate example. Show you a couple of. So here, the task that I've given myself is, how do I label the data set for the different room types? So can I create, look at an on-labeled data set like this, where ImageNet maybe is not the easiest thing to use as a pre-trained network. So I'm letting the system decide if there's something better and see if it can give me some clusters that would make it easy for me to label. And what I want to label is essentially the room type. So exterior, bedroom, bathroom, living room. So exterior obviously seems like it's pretty trivial. It's this part of the space. So anything that has a sky associated with it, outside walls, etc. That one is very easy to pick up. Okay, so let me go back to kind of the clumpy clusters that I like. Okay, here's one. Let me see what's in this part of the space. Looks like pretty much all bedroom. So you might ask yourself, well, how does it know? Maybe it doesn't have a bedroom class in the pre-trained network. What is it reacting to? It's essentially reacting to the shape of, the most common object that it sees here. In this case, it's a bed. So that's one. There seems to be a clustering here. Let's see what that one is about. Looks like these are all my kitchens. It might make some mistakes with kitchens and things that look like kitchen appliances, like these washer dryers. In Europe, unfortunately, the washer dryer can happen in hallways or in the kitchen itself. So those are things that I don't want to confuse my model with. Not sure what that one is. Looks like a kitchen sort of in the back of the image. Again, maybe not something I want to teach my model. Okay, and I'll say everything else is a kitchen. Let's go to this one here. Maybe do a gentle selection there. Looks like bathrooms, pretty much all of them with the exception of this one. Yeah, I guess that's a kitchen maybe. Yeah, that's something that looked like a bathtub probably to the model. So I'll say these are bathrooms. Rotate the perspective, see if there's a different one I want to use. And I'm doing this on my little monitor screen, on my laptop screen. So you're better off kind of using a much bigger screen to be able to see what these clusters are about. Oh, that's bedrooms, we got those, but let's make sure we got those. Yeah, so the different projections react to different things. Lisa, I think that's the kind of the unsupervised nature of this tool. You can see like there are some drawings here, and this particular projection is sensitive to those drawings and kind of clustered them. So it really gives you lots of different choices in the hope that one of these projections will resonate with the labeling task that you're interested in, essentially. Let me go through and try to. Okay, so it's interesting. Down here is a cluster of empty rooms. So this may be something I want to teach my model, that these are typically empty bedrooms. So I'll add that so it knows what to do with those images. What I'm looking for are living rooms, and actually you can see those are hard to find. There's maybe a clustering of them in here because there are things that have like dining chairs and tables, but those things can also happen outside of the unit, you know, things like this. So I can start my living room class with this, but I'm gonna need much better selections. And the way I can do that is actually maybe select a few of these. This is kind of a little trick I've learned. If I select a few of these, they have that outline on them now. And if I change the clusters, I'll see what direction do those tend to move, and are there additional ones in there that I may want to pick up, and sure enough, there are. So I can kind of trace how they're moving from projection to projection. You can see some are going to be, you know, pretty hard to select, while others are, you know, pretty conducive to just making clean selections. Looks like maybe this was one of the better perspectives. And then a couple are down here, maybe a few more. So I have to be gentle with this one because living room is maybe one of the harder classes. So I'll add those. And now I think I have enough that I can ask for a model to be trained. See how well it does based on these 5 classes that we've identified so far. Okay, it looks like we're at about 75% accuracy so far with the classes that we've created, which is to be expected. We only have a couple dozen. So the idea is that now we have a custom network for the task that we're working on. That's not bad. This may be actually like within 10 points of state of the art for this task. It's just telling us we need to do some more labeling for the different classes. And the projections that we'll get now are not coming from a transfer learning network. They're actually coming from the network that we've been training. And you can see how clean the clusters are. So there's very much a distinct group of outdoor clusters. There's this cluster here looks like all my bedrooms are tightly packed together. The ones that it's having trouble with are, you know, living room versus bathroom. And I can try to separate those by selecting the 2 classes and say, force these apart, find a perspective that has these as far apart as possible. And it's suggesting that I use this one to do additional labeling of that so that it can better separate those. In fact, I may do that. Yeah, I may just pick up a few more examples from here and add them to the library. So one question is, okay, so you train this model, but what is it useful for? What can you do with this model? The easiest thing I could do is predict the CSV, ask for a CSV file of prediction. So I've labeled a few hundred examples, but I can take this model and apply it to my entire data set and say, give me the predictions for the entire data set, even the examples that I haven't labeled based on the model that you've trained. So it constructs the CSV and downloads it for us. And I can open up that CSV, show you what that looks like. So it has the image name, the prediction, the image URL, and it should also give us the serving URLs, essentially, the globally accessible URLs for that image. So that's one of the first things I can do. I can also ask for a prediction API endpoint, give me a REST endpoint that we can use to you know, send in images and get back predictions. And then finally, what we're working on is to make this really easy for our users. We can generate a React Native app and tie it to this project so that you can just take a picture with your smartphone and get an instant prediction from the model that you've trained. So that's our goal, to make this as easy as possible for domain experts to make these kinds of models and be able to deploy them in production applications. So I'll go back now. A few of you had questions about how does this actually work. So let me tell you a little bit about what's going on behind the scenes. So as I said, we want to create this loop essentially where we lay out some data points for you, initially using the transfer learning model. You create some labels, you train a model by pushing that button. This creates a new model essentially that we can use to create a better layout, which hopefully helps you create even more labels. And this increases the accuracy of the next model that you trained. And you stay in this loop until you're satisfied with the accuracy that you're getting from your model essentially. And what's going on behind the scenes? Like what are the ideas, the research ideas or approaches that are making this possible? So first and foremost, something we don't take credit for is the power of human perception, right? The human eye is very capable of seeing patterns, seeing exceptions to patterns, and it's able to process that extremely well when you show the data in a certain way. Some of Jeremy's research, for example, suggests that you want to present a few big images along with lots of small images. We add an alpha effect based on the confidence interval of the model. So we're doing certain things to essentially leverage the power of human perception. Obviously transfer learning, but also being able to determine what's the right network for a given transfer learning task. Multiple labels, multi-class. I think you mean, Daryl, I think you mean multi-label, not multi-class. And right now, the tool only supports multi-class. We're in the process of looking at multi-label use cases, and sometimes we use multi-label trained networks for transfer learning, but the tool currently only does multi-class predictions, not multi-label. Okay, so transfer learning, as I said, we not only look at we look through in an automated fashion array of dozens of networks, and in the future, because we have this public edition of the tool, and lots of people will be building networks in lots of different domains, we hope that number will turn into hundreds or thousands of networks to determine what's the best transfer learning network to initialize your task. What we mean by active learning is one of the approaches we utilize is we not only create learning pressure from the algorithm based on the explicit labels that you give us, but also just the gestures and the interactions. If you came in here and you looked at this data set and you said, I don't want to classify that as part of this group, we're taking this as a negative example. And we might even put a certain weight on this, a higher weight on this than we would had you essentially selected this as part of the bathroom class, I guess. Yeah, so semi-supervised learning or meta learning is something that allows us to train these models pretty accurately with just a handful of a few dozen labels, and then noise resilient training techniques are put in here in case when you lasso, you pick up some unintended images. So going back to the three stated problems, right? That you need lots of labels to train deep learning models. You need domain expertise if you're working in a technical domain, and these approaches tend to be a domain expert working on a technical data set tends to be a slow and tedious process, introduces this like slow per label problem. We kind of mapped the research areas that we could work on to those three problems that we wanted to solve. And then one thing I'll mention is that if you looked at our pricing, you'll see a public version. The public version of the tool is essentially free for you to use. This one here. So we have a public edition. In this case, you always own the images. That's your IP. But if you use our public edition, essentially the models belong to platform and they can be used to bootstrap other problems. If you use the private edition of the tool, the paid edition, essentially both the data and the models, the derivative artifacts are yours, and we will not use those models to bootstrap other tasks. Okay, so that's the quick demo I wanted to share with you. And then let's maybe finish up by looking at some of the most recent research work that we've done. Some of you might be very active hands-on practitioners and might have a particular interest in these areas. So Jeremy and I have decided that we're going to essentially share all the knowledge of how we're building platform AI with the machine learning community, so that these techniques can be used even by data scientists and machine learning engineers, not just the domain experts that we're targeting with platform AI. So I'll just walk you through the 4 posts that are up on here. We're pretty much weekly adding new posts. This one was really around doing hyperparameter optimization. And you might have seen sort of the big iron approach that a lot of research organizations are using for hyperparameter tuning. Anything from Gaussian processes, tree of Parsons estimators, to evolutionary algorithms and reinforcement learning to essentially tune the hyperparameters of a neural net. Things like learning rate, the discriminative learning rates, weight decay, dropout rates, etc. And Jeremy's belief is that your networks, a good set of defaults ought to get you 80–90% of the way there. There should be very little hyperparameter tuning necessary in a tool, in these tools. And in fact, his work and Leslie Smith's work on using second-order derivatives to do things like one cycle have been really helpful in eliminating the a lot of the sort of the craft of doing hyperparameter tuning. So this was a study done by Fellowship AI Fellows where we looked at a variety of different data sets. We looked at the fast AI default hyperparameters essentially, and did some hyperparameter explorations to see sort of on a univariate basis if we try a different weight decay value, or if we change the atom beta 2 parameter to a different value, what effect does that have on the accuracy? And we tested that in a few-shot learning way where we only used like 20–30% of the data. And then we tested it on the full data set sort of to mimic the platform behavior. And what we found out is actually it's very hard to beat the platform fast AI defaults. They're very, very good. With the one exception, which is if you have data sets that are far from ImageNet, there is a distinction between the learning rates that you might want to use from the learning rate finder versus maybe 1 order magnitude smaller value than what the learning rate finder would have recommended. And we use this cosine similarity of an embedding from your data set and the transfer learning data set. So you can read about this. Basically, the happy news for Jeremy was that it's very hard for us to beat the fast AI hyperparameter search, which is great. We've done some work on augmentation searches. So before I train the entire network, how do I determine what are the right augmentations to use for this particular task? Again, the benchmark is the fast AI defaults. And we looked at a variety of ways. Again, we don't have the luxury of training the network, a variety of networks with all the different hyperparameter combinations. We looked at just a scenario where we could, before training, assess will this augmentation be helpful or not, were it to be used in training. And the way we did that is through test time augmentation. So we use the augmentation at test time, and then we said, look at the error rate that we get when you add this augmentation to TTA, and then, does it correlate with the error rate that you would get once you train the network? And it seems to be, there seems to be some correlation of the two. So we took this approach and actually applied it to a particular domain, which is Food 101. And with a fairly small network like the ResNet 50, we achieved a new state-of-the-art for top 1 accuracy. And we did it in a pretty elegant way compared to the 10 crop augmentations that were done in previous papers, or people came up with like custom networks. There was one that was using convolution and like different slices of the image in order to achieve the result, and they used dense nets and much larger networks than the one we ended up using. So the TTA approach that we have in the tool seems to be helping us create some state-of-the-art artifacts. And then, you know, one topic that we think about a lot is like the transfer learning, like having good networks to start out tasks. So in this case, we wanted to look at like celeb A facial attributes. So can we give you a network that would help you, if you have a face data set, can we help you create good projections? So like male versus female. And what we're doing here is comparing like our default model, which is ImageNet, to a specialized model, which in this case is a facial recognition model trained with this arc face loss, which is a state-of-the-art approach. And what we noticed that for some things like gender, ImageNet does just fine. Headwear, it does just fine. Hair color does okay. But for a lot of the more nuanced attributes like young versus old, attractive, unattractive, obviously very subjective date labels there. But you know, for at least from a celeb A perspective, there tends to be much better separation of the clusters when we use a facial recognition network versus just using ImageNet. So we're doing this kind of research on a lot of different domains. And one of the examples that I'll show you, if you're not squeamish, you can take a look at these burn images. If you are, please just look the other way or turn off your screen. But we're working with a plastic surgeon in LA that wants to build a burn application to diagnose the severity of the burn, whether it's a first degree, second degree, third degree, fourth degree, etc. And here we want to create a projection that would be helpful for him to do this kind of labeling. And this is one of the research areas that our fellows have been working on as well. So I'll show you some example projections that are starting to look pretty promising, even for a very technical task like that. Should be one projection shape that, yeah, I think this one here. You can see there's like sunburns here. I'm not going to zoom in too much to spare you the horror of these images, but blisters are over here, and things that are really badly burned, require surgery, are all down here. So even for something very technical, very specific to a domain like this, we're starting to see the promise that platform can create useful projections, particularly through the research work that our fellows are doing to assist in use cases like this. Okay, I'll pause there, and maybe for the remainder of the time, let you just ask questions, you know, particularly if you are wondering about how will this work in a given domain, you know, those kinds of things. I'm happy to share our experiences with you. And feel free to unmute and just ask a question. Might be a lot faster than typing it into the window. Lisa, what do you mean by detail the UI? Just kind of walk you through element by element what everything does? Oh, sure. Yeah, happy to. In fact, we should do a better job of documenting that. Let me open up STL again. Lisa, thanks for asking that question, by the way. So one button that I use quite a lot is this certainty button. So based on the model's confidence, we add an alpha value to these images. And what this is telling the user is essentially, don't bother labeling the things that are grayed out, because I'm pretty confident I know what those are. Focus your attention on the things that are a little bit darker. Those are the things that I need help with essentially, and that's what this button does. So right away, that's easy. And then obviously full screen, we have help. Those are self-explanatory. Let me focus on this part of the UI. Okay, yeah, let me come back to this. Let me just finish up detailing the UI. So lasso select, so by default, it's in pan mode. If you want to select, you have to turn that button on. When you select, you can bring up the gallery view like this. If you don't like that selection, you don't want to create a label from it, you would undo that selection with that button there. This will ask for 500 new random images in case you get tired of the ones you're looking at or you're not finding the kinds of examples that you're looking for. This will essentially bring up a new batch. That's the train. This is the prediction CSV download. If I zoom way back in or I pan kind of completely out and I lose where my data set was, I can just recenter everything with that. Down here are essentially the buttons to change the perspectives. And you can even name these. So you can say, this is, good one for finding trucks. And you can highlight, give it a highlight color. These are a little bit sort of faded, hard to see, but you can see that perspective now has a color and it's got a name. So it's easy for you to go back and find it in case you want to have it essentially bookmarked. Let me talk a little bit about what's going on here. So you can you can change the name of the class if you want to, like this. You can bring up the gallery of what's in that class by, unfortunately, a few clicks right now, but we're working on improving that. So you say edit label, and then you click on that icon and it'll bring this up. And in fact, it looks like I made some bad selections before, so I can fix that up and leave it only at horses as an example. But yeah, we've been trying to keep the UI pretty minimalistic. The idea is it's you and the images interacting together. We don't want to create the equivalent of a Photoshop with 1,000 options. We want to keep the UI pretty intuitive and streamlined. So if you have input for us in this area, we would very much appreciate it. Okay, so let me go in order of these questions. Different products on the shelf, angle from a security camera. Yeah, it's an interesting use case, actually. If you're willing to upload that data set and make it public, we're happy to look at it with you and see if we can help with that use case. Depending on if those products exist in ImageNet or not, that might have an effect on the clustering that you get. And also, we're working on different attention mechanisms. So the right attention mechanism might help give you the projection that you're looking for. So I would say it's not a use case we've tried. If you upload it, we're happy to look at it with you and try to make it work. Yeah, I appreciate the question regarding Radiology Quest. This is something that we plan to work on. We haven't gotten around to it. As I said, the first group of use cases in the medical domain have been related to things like burn and blood cells. But we will get around to some radiology and radiology images as well. It's something that Jeremy has done a lot of work on, obviously, from his background in analytic. Yeah, Lisa, thank you for that suggestion. That's a great suggestion. We're actually in the process of completely revamping our UI. And once that's done in the next few weeks, we're going to make some step-by-step demos, videos on how to use the new UI.
Ashok, thanks very much for this here, Roelof of Creative AI. Can you tell a little bit about the plans you might have for other kinds of data, be it like beyond images, like text or audio, but also beyond like image labeling, like maybe segmentation or things like this?
So great question. We have no plans beyond images, I would say. Like there are so many interesting problems for us to work on in the image domain that I think if we were to start working on some other form of data, it would feel like almost like a whole other company. So for now and for the foreseeable future, we're going to stay focused on images. The second part of that question is a very interesting topic, actually. We have some prototypes that we've been working on where the user provides image level annotation, exactly like what I've shown you today. But when we produce predictions, the predictions are bounding boxes and sometimes even like segmentation masks without the user having to give that kind of annotation to the data set, essentially. So you still do, lasso, create a single label for the image. But when we predict, we can say, yes, this is the bird class. And in fact, here's a bounding box for where the model thinks is that bird, or here's a segmentation map for that bird. That's an area of research that we want to put a lot of energy in because we think asking users to do the other kinds of annotation, people are spending 20 minutes per image doing segmentation masks right now, and that's not good use of a human. So that's something we definitely want to make it work for the domain experts that we're targeting. And we'll have some prototypes rolled out in the product in the first quarter, actually, at the end of the first quarter.
And more specific question about like segmentation. Do you think you're also looking at things like soft segmentation and like things like pixel RNN, where you kind of have user interaction of trying to first like make rough like segmentation maps, which then maybe get fed into a model to retune it or refine it, and you still can have this interaction between the system and a user whose time is valuable, but you can still guide it in the right way, which is of course much easier with like purely images.
Yeah, I totally understand what you're requesting, and there are products on the market already that do that. Things like Supervisely, I believe, do that kind of an approach. It's kind of not the direction we believe in, honestly, because as I said, a lot of the tasks we want to look at, like what's the final application that you want to build, and I think people often segment images at a very high level of precision, or at least try to. Unnecessarily to solve the task. So we're going to go in a different approach. We're going to stick with image level annotations and try to produce the best segmentation masks possible with that technique, and really try to advance the state of the art in that area. Because even with those kinds of soft suggests, it can be quite time consuming to fix up those soft suggests, and we can't find a way to automate that. Not automated, but make it something where you can do multiple images at a time. Like that is the philosophical basis of our tool: is don't label things one at a time. It's not good use of your time. Do batch labeling essentially, and we can't find a way to batch label that soft suggest segmentation approach that you described. So I think our research will probably take us in a different direction than those products.
Great, makes a lot of sense. Thanks.
Arshak, earlier, I think, and correct me if I'm wrong, but I thought you mentioned something regarding autonomous driving, and I was just wondering what the application of the platform is in that domain.
Yeah, some of the use cases we've looked at in AV so far are street signs, so being able to find street signs and classify them. Is this a speed limit sign, stop sign, U-turn sign, etc. We've also looked at a use case related to emergency vehicle identification. So finding, to give the AV a way to identify ambulances, fire trucks, police cars, etc. That's actually quite a challenging use case. There's not a lot of labeled data available for that. Often you can have a significant amount of occlusion, or the police car is really far away from the AV, but it already needs to know that there's a police car coming my way that I need to identify and start to pull over. So some of those are the initial set of use cases that we've seen in AV.
Gotcha.
Okay. Well, really appreciate everyone joining us today. We'll try to do this periodically as the tool advances, and please get in touch with us if there are any other specific questions that you'd like to ask. But thank you very much for spending an hour of your day on a Friday morning. Have a good weekend, everyone.